use the ratio test to find the radius and interval of convergence. Now, the idea here is that the ratio test says that a series converges if this limit is less than 1. So if we take that limit and then determine the x values where the limit is less than 1, then we should be converging. But what happens when we do the ratio test and we equal 1, right? When we take that limit and it equals 1, it's inconclusive, right? So now what we have to do is when we use the ratio test to find the interval and radius of convergence, we're going to have to check the endpoints. And the reason is because the ratio test is inconclusive if the limit as n approaches infinity of a sub n plus 1 over a sub n, get absolute value signs, equals 1, right? So we have to check those. So let's do an example. This is a power series. I can see the x minus 5 to the n. I also can tell that this is alternating, but this is not geometric in any way, right? This is not like a p-series scenario. This is a power series. So I'm going to use the ratio test to see where the interval of convergence lies. Now, hopefully you can tell by looking at this that the center is 5. That doesn't mean anything for my ratio test, but it's going to come into play later. So I'm going to start off by doing the limit as n goes to infinity of a sub n plus 1 over a sub n. Zoom in a little bit here. We're plugging in an n plus 1. Everywhere there's an n. Now, the good news about putting absolute value signs around this expression is that the negative 1 isn't going to do anything, right? So basically, this is a 1 and this is a 1, so it doesn't really do anything because it's negative or positive won't matter once it's in absolute value signs. So that's something to consider. Oh, let me get back to the right color here. N times 2 to the n. So I'm going to rewrite this without the 1s. And I'm going to make sure that I write it as multiplying by the reciprocal here. So I'm going to multiply this by n times 2 to the n. Then I've got x minus 5 to the n times n plus 1. Let me get that in parentheses. Times 2 to the n plus 1. Notice that this variable is an n. It's not an x. So I am going to reduce where things are reducible, but I am going to pay careful attention to that. So equals the limit as n goes to infinity. Let's reduce appropriately. So I've got x minus 5 left. I still have an n left. When I reduce the 2n and the 2n plus 1, this reduces to just a 2 on the bottom. So now this is 2, but this is still n plus 1. Anything that doesn't have an n is not going to be impacted by the limit. Technically, I can actually factor this out to the front. I really encourage kids to do that because I think sometimes it's tempting to plug in infinity, right, to kind of analyze infinity where x is. So I'm going to encourage you to move this to the front if necessary. All right, so I'm going to do equals x minus 5 over 2 times the limit as n goes to infinity of n over n plus 1. You do need the absolute value signs around the x minus 5 over 2. It's not going to matter if you put this in absolute value signs or not because this is all going to positive infinity anyway, so it's not going to change anything. So it looks like my result of the limit is 1. So I get the absolute value of x minus 5 over 2 times 1, which is obviously just the absolute value of x minus 5 over 2. Now, this is where you might be like, okay, what's next? Remember, this is a ratio test. So what we're saying is when this value is less than 1, I know that this series converges. So now I can check and solve for the x values that are going to make that happen. So we want to then take this expression and say, when is that less than 1? Because that's going to be where it converges. Okay, so let's make that note. Okay, so series will converge. Again, these are your notes, right? So we're trying to make sure that we understand why we're doing what we're doing. So now the job is to solve. Okay, so I'm going to solve this. Couple of ways that you can do this, but basically, remember the absolute value, if this is the absolute value of x, that's the same as the negative and positive, right? So there's a negative feature here. So just setting this less than 1 isn't enough. You have to say, okay, well, the negative is also part of that. So this is an inclusive inequality. So it's an and statement. So we can say x minus 5 over 2 is going to be between negative 1 and 1. I'll show you other ways to kind of decipher that as we go. But that's, remember, there's a negative and a positive feature to that absolute value. Okay, so now I'm going to be an algebra student for just a second. Let me kind of get this going. Multiply by 2. I'm setting this up as one inequality, but I could easily just do 2 of these if that's what I needed to do. And then we're going to add 5 to both sides. So we have 3 is less than x, which is less than 7. Now, this is kind of the interval, right? It's the framework. Let me make that note. This is the framework for the interval of convergence. Framework for interval of convergence. The question is, what is happening at 7 and at 3? So this is where we're going to have to test the endpoints. So I'm going to write a note here. All right, so now test endpoints. So what does that look like? Well, we're going to plug in a 3 for x back into this series, and we're going to use all that information that we used about ratio tests and geometric tests and p-series tests, because now it's not going to be a power series. It's going to be a series of constants. So let me do a little line here. We're going to say at x equals 7. I'm going to do 7 first. It's a little easier, to be honest with you. So let's plug that in. So n equals 1 to infinity. If you plug in a 7 for x, you're just going to get a 2 in that spot, and then you have n times 2 to the n. So before I start analyzing this series, I want to reduce as much as possible. That's 2 to the n, and that's 2 to the n. So what this series is negative 1 to the n plus 1 over n. I recognize that. That is the alternating harmonic series. Okay, so if this is alternating harmonic, you can build it if you need to, right? But it starts with that plugging in a 1, right? So we get negative 1 squared, so 1 over 1, and then minus 1 over 2, and then plus 1 over 3, etc. Now it does hit all my conditions, but I'm going to write out alternating harmonic. Therefore, at x equals 7, right, this series converges. So what we're saying is that this x equals 7 is in the interval. right? That's the concept. So now let's check to see what happens at 3. All right, let me draw a little line right here so we kind of have an idea of where my break is. Okay, so what's happening at x equals 3? This is going to take a little bit more manipulation here. You have to do this sum. You're not going to have to do this on every single question because there's other scenarios. But if you plug in a 3, now you're getting 3 minus 5. Now that's going to be a negative 2. So that's going to change how we approach this. So let's see if I can help make sense of this a little bit. So I've got negative 1 to the n plus 1. And then I have a negative 2 to the n. Okay, you cannot just reduce these, but you can use some algebra skills. So what we have here is a negative 1 to the n plus 1 times a negative 1 to the n times 2 to the n. You can break this up into negative 1 to the n and 2 to the n. So n, 2 to the n. So now I have some reducing happening. Now this, oh, sorry about that. This is the same base. What are you supposed to do with the exponents? Oh, you're supposed to add them. So now this is negative 1 to the 2n plus 1 over n. And when you start plugging in a 1 here, right, so this is going to be negative 1 cubed. Okay, then negative 1 to the 5th, and negative 1 to the 7th. So it's always negative. It's actually no longer alternating, which is kind of interesting because it is the negative of the harmonic series. And the negative doesn't impact this at all. So this is harmonic, right? Therefore, I'm just going to put therefore diverges at x equals 3 just to save room a little bit. So notice in all that analysis, I know it took a lot of work, but I'm going to include 7 in my interval. I am not going to include 3. So overall, after all that work, we can label our interval of convergence. So we can say interval of convergence. I'm going to abbreviate that real quick. It started like this, but now I want to include the 7. I am not going to include the 3. But no matter what I did in terms of the interval, the radius stays the same. So the radius of convergence, right, is still from the center, okay? So I've got the center would be 5, so I went 2 units this direction and 2 units this direction. So I can tell that the radius is 2. Whether or not these are included, that will have no impact. Okay, so the center is here, 2 to the right, 2 to the left, so the radius is 2. And then, of course, the interval is 3 to 7, and we include the 7.